Hi and welcome to video 15 on this series of Newton's laws and forces from Unit 4 Topic 2 of the Specialist Math curriculum. And I'm going to talk to you today just about variable forces, and it's the last part of this unit, and certainly in the order that I've taught it. So the exercise is completely complex based and it connects forces and if we have variable acceleration. Everything you might recall that we've done in the past is to do with if we have that static acceleration where acceleration is just a numerical value. So I'm going to do this through some examples, and we have to bring back those different variations of acceleration to complete these questions. So example 1, a car of mass 1600 kilograms is moving along a straight road at a speed of 90 kilometers per hour. When the driver brakes, the resistive braking force is that. So you can see this is what makes this question a bit different. And it's in kilonewtons as well, where t is the time in seconds after the brakes are applied. Calculate the time taken for the speed of the car to be reduced to 60 kilometers an hour and the distance travelled by the car in this time. So we're going to start with our answer to part A and bring it into part B, and we'll see how we go. So in A, we want to find t when v equals 60, so we need to find velocity as a function of time. So we're actually back before our force work, and we're looking at different variations of acceleration. So we know that our force that's given to us is 320 over t plus 2 cubed, and we know that that's kilonewtons. So we're going to make sure that we deal with the fact that it's in kilonewtons. I'll put a little kn there, and just remember that kilonewtons is equal to 1,000 newtons. 1 kilonewton is 1,000 newtons, but we'll deal with that a little bit later. We also know the mass of the car is 1600 kilograms, so we know therefore that MA equals 320 over t plus 2 cubed, and we know that 1600A equals 320 t plus 2 cubed. But now we've got kilonewtons against newtons, so if we add in that factor of 1,000, we can start to do something here. So what I'm going to do is I'm going to write down times by 1,000 newtons, and then I'm going to cancel that 1,000 out with this 1600, and it leaves me with 1.6a equals 320 over t plus 2 cubed, and dividing by 1.6 I get a is equal to 200 over t plus 2 cubed. So I've got my acceleration in terms of my time, and so now this is the bit where we have to go back to our work with acceleration and recognize that we know that dv dt therefore is equal to 200 over t plus 2 cubed, and so therefore the integral with respect to v is equal to 200, and I'm going to write like this, t plus 2 to the power of negative 3 dt, and we're integrating that, so we're solving this differential equation now, which means that our velocity is equal to 200 over negative 2 times by t plus 2 to the power of negative 2. So we divide by the new power, raise the power to negative 2, and we've got some constant. Now we also know that at t equals 0, v was equal to 90, and so we can, and this is 90 by the way, kilometers per hour, and we can deal with that, but of course we are dealing up here with an acceleration that is in meters per second squared, so we have to convert this kilometers per hour, and to do that we convert the kilometers into meters by multiplying by 1,000, divide by 60 and by 60, and this is 25 meters per second, and so we get 25 is equal to negative 100 times 0 plus 2 to the power of negative 2 plus c, and that actually 0 plus 2 to the power of negative 2 is a quarter, 1 over 2 squared, so 25 is equal to 25 plus c, and therefore c, now I have just missed a little trick here, because we're dealing with this, but c actually comes out as 0. I need to explain why now. If I go back up, don't forget that this force was a resistive force, so it's operating against the motion. So this is resistive. You may have been thinking that watching the video, why is he doing it like this? But our force is resistive, so the acceleration is resistive against the motion. So these are all negative. Now I could have fixed this much easier, of course, by accepting the fact that velocity is in a negative direction and the force is in the positive direction. That would have worked as well. But here we go. I've now got acceleration, so I've got velocity is equal to 100 over t plus 2 squared, and we want to find when the velocity is equal to 60. So when does v equal 60, and 60 times 1,000 divided by 60 divided by 60 is equal to 16 2/3 meters per second. And so I put in my 16 2/3 is equal to 100 over t plus 2 squared, which is now 16 2/3 is 50 over 3. It's probably going to be easier to deal with. T plus, that's a weird t in plus, so let's change it around. T plus 2 squared equals 100. Now dividing 100 by 50, I get 2 times by 3, that gives me a 6. So t plus 2 squared equals 6, and so therefore t is equal to the square root of 6 minus 2. And of course, plus or minus the square root of 6, but we're not going to have a negative time, so I'll leave it as positive, and that's approximately 0.45 seconds. It's small, but it's kind of what I was expecting, because that resistive force was quite high, like 320 kilonewtons over time, so I was expecting it to be pretty small. Part B of the question asks us to calculate the distance travelled in this time. So we have velocity with respect to time, and we have the time it happens, so let's determine the distance travelled. We just have to calculate how far it's travelled in this 0.45 seconds. So we can deal with this question by looking at the integral, because we know that this car started here and it's travelling in that direction. That's what the context provides us. So let's find the distance travelled by just simply integrating between root 6 minus 2 and 0, the velocity with respect to time between our two boundaries. And if we do that, we could do that on our calculator. We get 9.175 meters. That's how far it travelled in that time. Well, that's the end of example 1. So hopefully that was alright. All the best.